Large language models are here, and they're doing everything from writing our code to generating complex financial
They're
analysis.
incredibly powerful.
So powerful. But here is the central tension, the thing that I think keeps security teams up at night. Can we actually trust them?
That tension is absolutely foundational to deployment. When you have a probabilistic system handling secure data or, safety critical functions, a high confidence score is just not the same as a guarantee.
It's not the same thing.
Not at all. You need mathematically sound, certified assurances
Hmm.
about what the model will, or, and this is crucial, what it will not do.
Okay, let's unpack this. We've been immersed in this framework called BEAVER, which stands for an efficient deterministic LLM verifier.
Right.
And our mission today is to really analyze this research and figure out if it finally gives practitioners those sound, guaranteed probabilities about whether an LLM output will satisfy specific constraints.
To even understand the achievement here, you have to remember why verification for LLMs is such a notoriously difficult challenge.
It's the scale, right?
It's the scale and the nature of the models themselves. LLMs are autoregressive. They don't just spit out one final answer. They induce a probability distribution over a massive, massive universe of potential token sequences.
A statistical universe that just keeps growing with every single token.
Exactly. The vocabulary size alone can hit, 150,000 tokens?
Yeah.
As the sequence length increases, the space of all possible outputs just explodes combinatorially.
So if you tried to check every single possible valid response against a rule,
You'd be crunching numbers forever.
Yeah.
It's brute force impossible.
so we need to find the total probability mass of all compliant responses, but just searching for them exhaustively is completely out of the question.
And that's the gap that Beaver is designed to address. It provides the first, I think, practical framework for computing deterministic sound probability bounds on that satisfaction.
This isn't just a statistical estimate then?
No, not at all. It gives you a certified lower bound, PLB day, and an upper bound, PU. And that interval, that's the thing you can actually rely on.
That level of assurance is a total game changer. But, you can't get something for nothing in engineering. How do they even start to tame this combinatorial explosion?
It has to rely on a specific characteristic of the constraints being checked.
Okay.
It does. The entire system is built upon this core concept of a prefix-closed semantic constraint.
And a semantic constraint is what? Just a decidable rule? Like, does the output conform to the right format? Does it meet the functional requirements?
Correct. But the really critical insight here is the prefix closure property. And it's actually quite simple.
Hmm.
If a segment of the output breaks the rule, the rest of the output is guaranteed to break it too.
So once the constraint is violated, there is no coming back.
No coming back. That allows the system to hit the brakes early. If the model takes a wrong turn, the whole generation is useless immediately.
What's a good example?
Perfect examples are safety constraints, what they call 50 constraints for this thing, if you come with 50 pull list. If your constraint is do not generate toxic language, or do not generate dangerous shell commands, and the model generates the token arm-in
The violation happens right then and there.
instantly. Regardless of what comes next, the security constraint is broken.
But not all constraints work that way, do they? Give me an example of something that looks like a constraint but isn't prefix closed.
A classic one is a simple date format, say YYYMMDD. If the model just outputs the prefix 2024, well,
That's not a violation yet.
exactly. It isn't a complete date, but it hasn't violated the final constraint either. You can still complete it successfully.
So it's not a violation just because it's incomplete?
Right. However, and this is really clever, the Beaver researchers show how you can convert this. Instead of checking, is this sequence a valid date, you check if the partial sequence can be completed to satisfy the full requirement.
I see. So you're checking for the potential for completion.
And that conversion creates a prefix-closed variant. It's a workaround that makes a huge number of real-world constraints compatible with Beaver.
Okay, that clarifies the scope. So if prefix closure is the foundation, what does that foundation let them build that, fundamentally breaks with their old habits, like rejection sampling?
Right, rejection sampling, or S, it's the standard baseline. Just generate sequences randomly until you find one that works.
It's super inefficient.
It's plagued by two core inefficiencies that Beaver just systematically avoids.
Where do they save the most computational budget?
Well, first, there's the duplicate problem.
Mm.
RS involves these expensive forward passes on the LLM, and because sampling is random, you repeatedly waste budget checking the exact same high probability sequences over and over again.
Oh, right.
In one of their examples with bash commands, they found that sampling 10 times only resulted in 3 unique safe sequences.
7 of them were duplicates. What a waste.
Exactly. You're paying the cost for the same information repeatedly. And second, there's the late pruning problem, which is tied directly back to that prefix closure idea.
Okay.
RS has to generate a full sequence, complete with the end of sequence token, before it can check the constraint.
So if the model starts with a dangerous token, like pseudo or arm,
RS still wastes, dollar steps generating the entire unsafe command before it finally flags the violation at the very end.
so to sum it up, RS is slow because it samples the same safe paths over and over, and it's wasteful because it explores all these doomed unsafe paths all the way to the end.
Precisely. And Beaver just bypasses both of those problems through systematic search and really aggressive pruning.
Here's where it gets really interesting because Beaver doesn't rely on random chance. It uses this kind of structural exploration. How does it manage to map out the safe outcomes while just ignoring that massive universe of unsafe options?
It does this by maintaining 2 really crucial data structures that are basically tracking the safe search space.
Okay, let's call them the map and the compass.
That's a good analogy. First, the map. That's the token tree, or math county. This is a tree that explicitly tracks all the explored, constraint-satisfying prefixes, and it stores the probability of reaching each one.
So the trie only contains paths that haven't failed the constraint yet?
Exactly. And the compass. That's the frontier. This is the set of all the leaf nodes in the triso, the edges of our safe map.
And that's split into 2 parts.
Right. You have complete leaves, which are valid sequences that are finished, and incomplete leaves, which are sequences that could still be continued.
So walk us through the iteration. How does the algorithm decide where to search next on that map?
It's a simple 3-step loop. Step 1 is select. You pick an incomplete sequence, COAs from the frontier. And they found the most efficient way to do this is a greedy heuristic they call max mu.
Which means?
You just choose the sequence with the highest total path probability found so far.
That sounds sensible. You're prioritizing the most likely outcomes. It's almost like a guided beam search, but it's focused only on certainty.
That's the idea. Step 2 is expand. You do a single forward pass to get the next token distribution. And crucially, you only consider continuations that satisfy that prefix close constraint, finables.
Ah, and this is the aggressive pruning step.
This is it. If a token like RM violates the safety constraint, it is never even added as a child node. That entire dangerous subtree is pruned instantly.
So unlike RS, which wastes, a dozen forward passes on an RM sequence, Beaver rules that whole path out after just 1 step.
That's the enormous efficiency gain. It saves hundreds of thousands, maybe millions of branches of the search space instantly because of that prefix closure rule.
And the 3rd step.
Step 3 is update bounds. This is where you get the mathematical guarantee. The certified lower bound, PLB-DOL, just sums the probabilities of all the sequences in the complete frontier. That is the probability mass we have certified as fully safe.
And if I'm getting this, PUB is the maximum possible safety score, right?
Yeah.
The truth is guaranteed to be somewhere in that window.
Precisely. PUB sums the probabilities of all the nodes in the frontier, both complete and incomplete. It's the ultimate optimist score. It treats every incomplete sequence as if it will eventually satisfy the constraint.
And with every iteration, those bounds get tighter and tighter.
They monotonically tighten, which provides that crucial anytime guarantee.
That's so powerful. A practitioner can just stop the computation at any point and still report a sound probability interval to their auditor or their boss.
Yep.
Let's move to the results then. What did this systematic search actually uncover in practice?
So the researchers tested Beaver across 3 really vital deployment scenarios.
Yeah.
First was correctness verification for complex symbolic math reasoning.
Making sure the answer was right.
Right, ensuring the output was both grammatically correct and, functionally sound. Second was privacy verification.
Which is a huge one.
A huge one. Checking for models leaking known sensitive information, specifically from the Enron email dataset, which is a good proxy for any leaked PII.
And the 3rd.
Secure code generation, using a test called CyberSysEO. They tested Rust code completions, but under adversarial prompts designed to encourage insecure code.
So they were really stress testing it.
Very much so. The constraint was the absence of known security vulnerabilities.
Okay, so what were the key takeaways on performance? How did it do?
The first one was just bound tightness. On that math task, Beaver achieved 6 to 8 times tighter probability gaps than rejection sampling.
6 to 8 times.
Yeah. For the Quinn34B model, the uncertainty gap shrank from 0.092 all the way down to a razor-thin 0.013.
We're not talking about incremental gains here. That's an eightfold increase in the certainty you have about your model's output.
Correct. But the second metric, the risky distribution ratio, or RDR, reveals the most important practical finding for safety.
And what does that measure?
RDR measures the proportion of tasks where the probability of violation is non-trivial, say, greater than 10%.
The punchline here for anyone building safety systems must be that rejection sampling creates a false confidence.
That is exactly it. Take the email leakage task. When they tested Qwen34B, rejection sampling flagged 15 out of 100 scenarios as risky.
Okay, so an engineer looks at that 15% rate and thinks, okay, we're mostly safe.
But BEAVER, with its certified bounds, shows a totally different picture.
How did
It jumps from 15% to 67%. It identified 67 out of 100 tasks as having a non-trivial chance of leaking data.
Wow.
RS told you, you have a small leak. BEAVER effectively shouted, your privacy dam is collapsing. And that difference is why this kind of verification is non-negotiable in critical systems.
That is just staggering. It exposes this massive hidden privacy vulnerability that relying on traditional statistical methods would have completely masked.
And the findings were even more stark in the secure code generation task, especially under that adversarial pressure.
Let me guess, RS barely noticed a problem.
For one of the models, rejection sampling found only 2 risky instances out of 204. BEAVER, using its much tighter bounds, found 86 risky instances.
That's 42% of the total.
Exactly. So RS suggested a near-zero security risk, while BEAVER demonstrated that nearly half of the completions had a significant probability of generating vulnerable code when pushed.
Loose bounds don't just reduce accuracy, they actively encourage dangerous risk assessment.
They do. They give engineers a totally unfounded sense of security.
Let's talk optimization for a second. Was there a deployment setting they found that dramatically influences how fast BEAVER can tighten those bounds?
Yes, the decoding temperature proved absolutely crucial.
So a lower temperature sharpens the probability distribution.
It concentrates the probability mass on just a few high likelihood tokens. And what happens when BEAVER runs against a sharper distribution?
The search gets easier.
It dramatically accelerates convergence and results in substantially tighter bounds. Because that mass is so concentrated, the maximum greedy strategy resolves the uncertain probability mass much, much faster.
That's a key design insight for anyone implementing this. How dramatic was the effect?
Very. For that Qwen34B model on the math task, the bound gap was 0.013 at the default temperature of 1.0. When they lowered it to 0.33, the gap shrank to just 0.001.
Wow.
That lower temperature makes verification not just possible, but orders of magnitude more efficient and precise.
Okay, before we conclude, you have to remind us that no system is perfect. What are the current limitations of BEAVER?
Of course. And thinking about the limitations is critical. First, it is strictly limited to those prefix-closed semantic constraints we talked about at the beginning.
So for other types of constraints, like ones that only evaluate the final output as a whole,
It wouldn't work. New principles would be required for those.
and the second major limitation restricts who can even use the tool.
It does. It requires white box access to the model internals. Specifically, you need to see the full, unprocessed probability distribution for every single token generation step.
Which means you can't use BEAVER to verify a proprietary black box API model.
Or any model where sampling noise has been intentionally added. It's a powerful tool, but it is one designed for developers, safety auditors, or anyone with deep internal control over the model weights and the deployment pipeline.
It's a tool for the owner, not the end user.
Exactly.
This whole deep dive into BEAVER, it really shows a fundamental shift. For years, I think people just accepted that LLM behavior was too wild, too probabilistic to ever offer deterministic guarantees on safety or compliance.
And BEAVER establishes that systematic, deterministic verification of LLM constraint satisfaction is not some academic impossibility. It's both feasible and practical for deployment in real-world systems, provided you can leverage the structure of prefix closure.
It replaces statistical guesswork with certified knowledge.
It really does.
And that ability to replace vague estimates with a guaranteed range allows safety-sensitive applications, from finance to cybersecurity, to finally characterize and manage model risk with actual, provable confidence.
Since we saw that lowering the decoding temperature so dramatically tightens the verification bounds by concentrating that probability mass, how might we rethink the default deployment settings for LLMs in safety-critical applications? Maybe we should prioritize verifiability and guaranteed safety over just getting diversity of output. That seems like a crucial question to explore as these models move into regulated environments.